In the control rule, we talked about AIMD. We increase the window by 1 MSS every RTT. That means it can take time till we get the optimal window size, especially if we start doing that from the beginning. Meaning that we're wasting precious time until we fill the entire bandwidth. So, in order to do that faster, a stage called slow start is put in. What happens during slow start? We start with a 1 MSS CWND size, and it's multiplied by 2 every RTT. That means it grows exponentially. It grows faster than additive increase. How does it work? Every acknowledgement of a segment we get, we increase CWND by 2. That means that within an RTT, the window will be doubled. What does it mean? It means that at the beginning, transmission rates are low. That's why it's called slow start. And then it grows exponentially fast. Until when does it grow exponentially? We'll get there in a moment. Let's look at an example of transmission between host A and host B and understand how the slow start works. So at first, a single segment is sent from A to B because the window size, CWND, is exactly 1 MSS. This segment is acknowledged. It takes an RTT until the acknowledgement reaches host A. Then the window is doubled and 2 segments are sent. And then 2 acknowledgements are received. So, after receiving the initial segment, 2 new segments go out, and so on. After every RTT, the window doubles in size. This is the nature of slow start. Again, why did we introduce it? In order to use bandwidth as quick as possible, since the transmission rate increase is exponential. We said that packet dropping is precisely the implicit trigger to understand that our network is running out of its resources. That is, we understand there is congestion in the network. What is the reaction of the congestion control to packet drops? One of the implementations we can have is this. The moment a timeout happens, that is, that we didn't get a packet within a certain time, the CWND will decrease to be equal to the size of a single MSS. So we begin with the slow start, which starts growing exponentially. Again, there is a limit of the congestion window where we want to stop, an optimal window size. At some point, we need to stop the slow start and try to approach the optimal size more gently. We need to switch from exponential growth to a more gentle additive growth, meaning we reach a threshold called slow start threshold. And from there, the window starts growing with linear growth. That's how it works in the case of a drop, a timeout. We can look at loss. We can look at it as 3 duplicate acts. We talked about this optimization when we talked about implementing reliability. That's exactly what TCP/Reno algorithm does. It says that duplicate acknowledgements says that packets are still traveling in the network. That means part of the segments reach their destination. So there's no point to start everything from a single MSS. So in this case, we activate the multiplicative decrease stage. That means we're decreasing the window by half. So from that moment, the window's growth is linear, meaning we're implementing additive increase. That is the difference. In the case of a timeout, the size of the congestion window, the CWND, will be a single MSS. If we look and reach a conclusion that we get 3 duplicate acts, then we assume there's a loss. But still, because the acknowledgements pass, the duplicate acknowledgements arrive as a result of receiving segments, meaning that the segments are received, there is no point in starting the congestion window from 1, because it'll take time till we use the entire bandwidth. This is the reason we decrease it by half and not start at 1. From there, the congestion window's growth is linear. Now, unlike TCP/Reno, TCP/Tahoe algorithm always starts with a congestion window equal to 1, whether as a result of a timeout or as a result of 3 duplicate acts. By the way, that doesn't mean that in every situation TCP Reno is better than TCP Tahoe. TCP Tahoe is more pessimistic, and TCP Reno is more optimistic. That means that after we get 3 duplicate acts, it thinks the situation should be resolved by cutting the CWND in half window and then grows linearly. And TCP Tahoe just starts from the beginning.